Hey guys, today I'm going to talk to you about a mathematical principle which is pretty much my favorite in all of math. It's called Euler's identity. Euler spelled E-U-L-E-E-R. Wait, E-U-L-E. E-U-L-E-R. Yeah, Euler. And basically, the first thing you need to know for this principle is something called the Maclaurin Series. Now, I'm going to show you something that looks complicated but really isn't that hard, alright? If you just look at this, just take a minute to absorb it. So basically what this is it's saying that this function is going to equal an infinite sum of this thing, which is x to the n, which is that, over n factorial, which is f to the blank derivative, to the n derivative of 0. Now, what this basically allows you to do is to find the function of any one given graph if you know the derivative, every single derivative, meaning first, second, third, all the way to infinitieth of one point in a graph. All right. Now keep that in mind. So let's do this for something like E, right? So e to the x, right? Derivative of that in relation to x ends up just equaling e to the x. It's always going to equal e to the x. So if we plug it into our summation here, we can say that e to the x equals the summation, and equals 0 to infinity of f which would just be fn of 0 times x to the n over n factorial. Now, you can say for this though is that, so let's just solve the, let's just kind of write down the first few terms of this. Right? So let's just say let's just solve for where n is 0, okay? That's going to be just f of 0, which is just going to be e to the x, right? Of 0, so e to the 0 is just going to equal 1 times x to the n, which is 0, 1 over 0, that doesn't really work because factorial of 0 is equal to 1, so we end up with 1 as our first term. Then you're going to add that to the derivative of that, which ends up just equaling this, which is just going to equal e to the x at 0, which is 1 times 1 x to the 1, which is just x over 1 factorial, which is 1, so you end up with x. Now you do this again at 2, you end up with e to the x, which is 1 times 2 x squared over 2 factorial. Now let's just write the next few terms: x cubed over 3 factorial plus x to the 4th over 4 factorial. Right? Now, let's do this for a different thing. Well, actually, first you can also use something else to solve for e, because you can just end up saying where you could just get rid of the x and you end up with e equals 1 plus 1 over 2 plus 1 over 3 factorial plus 1 over 4 factorial. You can just do that forever. And that's your definition of e, which ends up being 2.718281828 something something something. Alright. Let's do this for sine of x. So sine at 0 is just gonna equal 0. So we have an expression of 0, so we can just skip that. The derivative of sine, though, however, is going to be cosine. So cosine at 0 is going to equal 1. Okay? And then you have x, so you just have a 1x over 1, so it's x. Then you get your second derivative, which is just going to be a negative sign. Right, so that's just 0 again. We go back to, and then we go to negative cosine. Right, which is that's gonna be negative 1 instead, and you're gonna have and you're gonna end up having this x cubed over 3 factorial. So that positive sign doesn't actually exist. So it's x cubed over 3 factorial. We do that again. We take another derivative of that. We end up with sine of x again. Right, no. So we left off with that, and we end up with just x to the 5th over 5 factorial plus x to the 7th over 7 factorial plus x to the 9th over 9 factorial, and so on and so forth. And that just the positive and negative just keep alternating, actually. Let's do this for cosine instead. So that's at 0, that ends up just being 1. That's 1 over 1, so that doesn't matter. And then at 1, it's gonna end up equaling so the derivative of cosine of x is going to equal negative sine, which is actually just for 0, it's just 0. So then we can go to negative cosine, because we get negative 1 times you get negative 1 times x squared over 2 factorial. And then we end up just doing that again, and then you see a similar pattern as up here. So that's, which is x to the 4th over 4 factorial plus x to the 6th over 6 factorial plus x to the 8 over 8 factorial. Right? Now, if you look at something else, you can say that now what would be e to the ix, I ask you? Well, you just replace everywhere there's an x with ix, so it's 1 plus ix minus x squared over 2 factorial minus x cubed over 3 factorial plus x to the 4th over 4 factorial ... See? Now, if you just now here's the interesting thing. If you look at this, cosine actually matches up perfectly with this. So you can say e to the ix equals cosine of x plus something to do with sine. So what are you gonna do here? Now, if you notice, it's just adding an I to each sine expression. And so you can just say I sine of x, and then you added I to all these. right? So you can say I times sine of x. Now, this is an incredibly interesting equation, right? Now, what happens if we say it's in radians? Say e to the pi I equals cosine of pi plus I sine of pi. Now, sine of pi is just gonna end up equaling 0, right? If we think about our unit circle, so that ends up equaling 0. Cosine of pi, however, is going to equal -1. So we end up with e to the pi I equals -1, or even better, e to the pi I plus 1 equals 0. And that is Euler's identity. Beautiful. A beautiful equation that is worthy of praise throughout the nations. Thank you.